Let's go ahead and get started here. First off, the recordings look like I took a look at them. They seem everything legible. Everybody's able to follow along and everything. Seems like that's working all right. If anything, maybe a little bit better because it'll actually capture my hand motions instead of me just the audio. All right, then let's talk about the quiz. So random quiz questions, icebreakers. What else can we do to extend the shelf life of pharmaceuticals other than decreasing the temperature? Decreasing the temperature is the #1 thing. Right. The more you can keep things, and that's why if it's something long-term and if it's something dry, recommend just put it in a Ziploc bag and throw it in your freezer. If it's a liquid, like a suspension or something like that, you can't really do that. So then you have to keep it in liquids, or a fridge helps, things like that. If you notice behind the desk at the pharmacy, they've got a freezer and a fridge right next to each other that they monitor the temperature of very closely. That's why. Other than that, the bigger, maybe not bigger, but equally big thing is just limiting oxygen. Keep it closed. That's why I didn't say throw it in a Ziploc bag when you throw it in your freezer. It's also to give it an extra layer of oxygen prevention. Because the #1 thing that's going to go wrong with it is oxidation. Sometimes it's going to relax back into some more stable state. Aspirin in particular does that. Aspirin is acetyl salicylic acid, which looks like, see if I can draw this one from memory. So I think salicylic acid looks like this. And acetyl salicylic acid puts in an acetate group either here or there. I think here. So we'd be. So salicylic acid is relatively stable, commonly found in lots of naturally occurring places, most particularly in North America, and willow bark. So if you've ever heard of a willow bark tea for as a pain reliever for a headache remedy, you can chew the bark, or you can chew the bark. That's actually has basis in science. You're getting some salicylic acid, which is a mild NSAID. So good for inflammation, good for fever reducing, things like that. Acetyl salicylic acid doesn't occur in nature and is even better. This is aspirin. If you leave this, just in general, if you just leave this long enough, it'll relax back to being acetate and salicylic acid. So you just wind up going back to the less strong version of it. Still not a bad thing. So expired aspirin is not something you really need to worry about. Some things, when they expire, they actually wind up making things that are worse for you. So you do have to be careful with expired medications in some cases, especially until you know the specifics of that pharmaceutical, unless you do some research. It doesn't have to be extensive research. Usually somebody's looked at this and say, okay, well, the expiration date, they always say the expiration date on anything from the pharmacy is always a year after you get it, right? Some things actually last significantly longer than that, especially if you keep it in the fridge. And they don't disappear all at once, right? It's an ongoing process. They've lost their labeled efficacy maybe a year after you've gotten them, but they're still 75% effective for the next year. And there's a half-life associated with these things, right? It's a first order process, just like from Gen Chem. But the main,
you got to possibly pretty 90%.
Depending on what the pharmaceutical is and the temperature is, especially something that says it has to be kept in the fridge. If you leave it at room temperature, it's like milk, right, or eggs. Everything by dropping the temperature, you rate by a significant portion. The exact amount you drop it depends a little bit on what the mechanism is and what the activation energy is. Remember, your rate constants follow the same rules. Are the same form of the equation as the equilibrium constant. It's just E to the activation energy over RT. So change your temperature, you're going to change your rate constant, but change your activation energy, you change it too. And this still is only looking at chemical breakdown. So something like eggs or milk, where you actually have a biological side of things, that totally throws all that out the window. And you know, you can't expect biological systems to follow something this simple. I had a group that did for their Gen Chem research project, they made a batch of beer and they were trying to track the kinetics of it. They measured the gravity of it every day for 2 weeks while it fermented. I basically came to the conclusion that you can't use chemical reads because it's a biological system. Well, it was a fun project. They enjoyed it.
I don't know if I worded this properly, but
No, not. I could see what you're saying. Could you recover anything,
yeah,
to recycle it? In theory, you can get the metallic mercury out, and which then you could process and turn it back into mercury acetate. So yeah, in a lot of cases you can, it's just that there's gonna be other stuff in there as well. So it's, and frankly, I'm basically recovering the mercury and then just getting rid of the rest of your waste is gonna be the most effective, both economically and just in terms of what's easy to find. It's not hard to find acetate or any of these other things. It's mainly the mercury that causes the problems with waste disposal, and then it's hardest to find. So as long as you can recover your mercury, that's actually a pretty efficient system from a chemical point of view.
how would you pull it out, like precipitating it with something or?
Probably precipitate with some, either once you get your product out, you could then oxidize the mercury, so it's mercury 2 again, which has really low solubilities, and turn it into a mercury salt by precipitating it out that way. It does wind up, you'll actually see this, there's a test that gets used. I guess that's silver. There are certain chemical tests where you're testing for specific functional groups, and what there, in particular, there's the Tollens silver mirror test uses silver acetate. And it'll reduce the silver to silver metal in the presence of a primary or secondary alcohol, but not a tertiary alcohol and not a phenolic alcohol. And when you do that, you just actually make silver metal. It actually like plates the inside of the round bottom flask. It's actually really cool to see.
So it looks like a mirror.
It looks, that's why they call it the silver mirror test. And so they would do something similar with that, dump it all out and then try to recover the silver by oxidizing it again, getting it dissolved again. That's a pretty, it's really obvious that you want to do that with stuff like heavy metals or with like precious metals like silver or gold. You don't want to have to keep buying that stuff because it's expensive.
For this question, I was thinking more like limited resources could make it like.
Yeah, ongoing.
Process.
It would be, and I mean, if you're gonna say a continuous process,
Oh,
with an engineer that has a specific.
I know.
So I was going down that rabbit hole. Yeah, you probably could. You're gonna lose a little bit. You're never gonna get perfect efficiency, but you could stretch your mercury by reusing it, by oxidizing, reducing it, re-preparing it. You probably get maybe 3 or 4 times without adding any more, but you're gonna lose some mercury every time. So your efficiency then is either gonna go down or you're gonna have to supplement it. But that's a pretty normal thing to pay attention to. And that is more on the engineering side than the actual scientist side, because the scientists don't want to mess with, well, I recovered this mercury to save myself some money, but now I don't know what's in it. Scientists don't want to deal with that. Engineers, where they're worried about, or somebody who's doing this out of their kitchen making meth or something like that, they're the ones that are doing that and making, and getting who knows what in their next batch. But that's, again, it's a pretty common thing to pay attention to. Thought we'd go through the quiz questions in general. So I've graded 2 of your 4. I looked at everybody's questions, but I haven't finalized the grades. Quick note about these ones where we got a bunch of questions that are all a file upload. If you do everything on one piece of paper and take one picture, submit just one picture to question 1, that's totally fine too. As long as I can read it, you don't need a separate file for every question. If that's easier for you to do that, that's fine, but it's easier for me to grade if it's all one file too, so
I broke it up into
a couple.
two.
Whatever makes sense, yeah, whatever fits and is legible, that's
Just
the main
saying.
thing, yeah.
Definitely.
Um,
One file from now on. Seven.
Yeah, and the main thing I don't want is for you to write it really small on a piece of paper, take a fuzzy picture from this far away where I can't see any of them. That's the worst case. I'd rather have more files, but. The main thing that I expected people to miss, that I did see, is that for these two, we had rearrangements. They're methyl rearrangements, so they weren't as obvious, but remember with these acid catalyzed ones. This is an acid catalyzed hydration, this is acid catalyzed called hydrobromination. So we had a hydrogen to one side and bromine to the other side. But for both of them, because they're acid catalyzed and they're gonna go through that carbocation intermediate, we gotta think about rearrangements. There's no hydrogens here. So when you do make that carbocation, we're gonna wind up with a positive charge here. What, if there's no hydrogens here, we can see a methyl move over. Nothing larger than a methyl, and we're not gonna deal with any ring shifts. In theory, you could also have something like this whole bond moved over, and then we have a 7-sided ring instead of a 6-sided ring. That's even slower and a little bit less favorable. So for the most part, we're just looking at the hydride shifts and methyl shifts.
If that methyl group wasn't there, then in theory, the product you would get would be like from the tropylium 7-member ring thing.
If the methyl wasn't there, there'd be a hydrogen there, and then the hydrogen would just move
yeah.
over. So it'd be more like if there was really no other option.
Okay.
You can see stuff like that, but if that's on more of a case by case basis. Because that being so slow means it really does depend on how fast the second step is.
Right.
If you can get a rearrangement before the next step comes in. So that's just exactly. That's just gonna be something that's a little bit less certain. So our final product here then is with the methyl moved over. And your OH is here, and it's not a chiral center. And because both directions around the ring are the same. Same thing here. I didn't mean to ask two questions that both had methyl shifts involved, but it's the same thing. We get a carbocation here, no hydrogens adjacent, but a methyl could move over. And when the methyl moves over, so we actually wind up with not OH. And in this case, do we have any chiral centers? It looks on the face like you might have as many as 2, but both of these methyls are identical. Both of these methyls are identical. As long as we have 2 identical things attached to each carbon, this is actually not a stereoisomer, or does not have a stereoisomer. Anything tricky about this one? You don't know?
No, it's not a trick question.
Be any sort of number.
Yeah, we're already gonna make a tertiary carbocation, so no rearrangements necessary. So no, so it's just gonna be hydrobromine here. It is Markovnikov.
Right.
In terms of we're adding the bromine to the more substituted carbon. So
I
final
just
product.
totally forgot on the quiz that there was the methyl and hydro everything.
Yeah, no worries. It's a normal thing. That's why we were practicing it.
I asked him.
I'm pretty sure there isn't, maybe,
I
but
looked it up online and everything seemed to line up, but.
Yeah, it's just with these acid catalyzed ones in
the
particular.
acid catalyzed.
Yeah, I looked up acid catalyzed. Hydrogenation and then acid catalyzed
Hydration.
hydration.
Yeah.
Both of those, and then all seem to line up.
Yeah.
Not very much.
Just those rearrangements. And that's why it was only a quarter point off, if you forgot the rearrangement, but you did everything else right. It's just mainly a reminder, I don't want you to forget that happens.
Yeah.
This is the worst eraser I've seen in a long time.
It's like a marker, it's just.
Yeah.
Have we learned any mechanisms that result in anti-Markov yet?
That's gonna be our
That's
first
gonna be
new one
today.
today.
Okay, yeah. Trying to keep all the things straight.
Yeah. And that's one of the primary like categorization, we're gonna do a lot with hydration, we do a lot with alcohols in general, because alcohols wind up showing up everywhere and both in biochemistry and pharmaceuticals, et cetera. And so we're gonna do a lot with hydrations, and we're gonna have our very specific. Here's Markovnikov hydration with rearrangement, here's Markovnikov hydration, no rearrangement, here's anti-Markovnikov hydration, no rearrangement. Things like that. Here is our Markovnikov, no rearrangement hydration. For this one, and it's adding ethanol and adding ethylamine for the second one. They all do the same thing, right? No rearrangement necessary, it's Markovnikov, just watch your nucleophile. So we're gonna come in and add an OH to the more substituted carbon. And the hydrogen to the less substituted carbon. So. There's our product. If you wanted to show the new hydrogen bond, you could draw it in there specifically, not required. R plus S, do we need to worry about stereochemistry? As long as these methyls are completely opposite, as soon as the methyls are there, then we get an R plus S, but because it's symmetrical each direction around the ring, we don't need to worry about it. Same thing with an ethanol, right? So we're adding an ethoxy group to carbon 2. Or right in keywords, what do you think? And here we're adding the nitrogen, and these are both symmetrical, right? There's no difference in the substitution for either of those. So we're just have to pay attention to stereochemistry. We are going to get 2 stereo centers out of this one, which means we could get a total of, I guess, we're still only going to get 2 stereoisomers because that second step of adding the hydrogen and replacing the mercury. This is a detail that we didn't go into explicitly, so I'm not going to grade you on this aspect of it. It seems like there's 4 stereoisomers, right? But we're only going to get the very specifically the ones that involve this is called a syn addition, SYN. Because we wind up adding both of our pieces to the same side. And that we can actually see why that would be the case. Because if we look at the intermediate, so our intermediate first step is break this and add our mercury, right? And the nature of this mercury intermediate means mercury has, if we're making this 3-sided ring, the mercury ion or the mercury piece has to be on the same side of the ring, it has to be cis. Which means these 2 methyls are cis relative to each other as well, right? And then second step is your nucleophile comes in here and has to do an SN2 to break one of these, right? Which then makes our second intermediate, the mercury and the nitrogen are trans. And then the last step, so then we wind up with. So mercury up. And the methyl up. Right, because we had to do that umbrella flip to bring the nitrogen in here. So then our nitrogen,
And is that methyl where the mercury is still there?
and yeah, so then the other methyl is downward.
Okay, so this is what I was having, that's why I asked if we can go over this question specifically, because I was having a little bit of trouble with this.
So our second intermediate
Mhm.
looks like this with the nitrogen and the mercury trans relative to each other. And then since our last step is to remove the mercury with that with the reduction with the hydride source. That hydride is gonna do another SN2, so we get two SN2s in a row. So the net result is that the hydrogen and the nitrogen are added to the same side. Which keeps the methyls cis relative to each other as well. So because it's an addition where where both sides of the addition are adding the same direction, they call that syn. SYN. If we added the nitrogen up and the hydrogen down, that would be an anti-addition. So same root as synonym and antonym, right? Ant means opposite, syn means the same.
So the methyl groups in the product are gonna be syn,
Yeah, because this is gonna be, we have the methyl group out. When this comes in and pushes the mercury off, it's gonna flip this one to SN2 again. This is why we spent so much time on SN1 and SN2. Because all of our same rules are still applying here, right? We're just doing them in sequence now, in a lot of ways. It's still our 4 basic mechanism steps. Proton transfer, nucleophilic attack, rearrangements, and leaving group leaves. Those are almost all of our arrows are gonna be one of those 4 things still right now, right? Exactly, exactly. And so net result is we do wind up with 2 stereoisomers, but it's the 2 stereoisomers that allow the methyls to both be on the same direction, so no diastereomers. We could add. So final result, that's our methyl. I guess I'm not gonna draw, to avoid making this look more complicated. I'm not gonna draw hydrogen, so that's our methyl. That's our other methyl, and then out of the board we have our methylamine group.
You would get.
And then we get the mirror image of that as well.
Yeah, I see.
Right, so the mirror image of that still has both methyls on the same side of the ring. They're just coming out instead of going in. All right. So oxymercuration has its wrinkles, but the nice thing about it is it's very specific, right? So we don't need to worry about rearrangements, and we're going to get a limited number of products that way. Acid catalyzed is a lot less discriminating, just like SN2 versus SN1, right? SN2 only made very specific products. SN1, you could wind up with a mess of things because of rearrangements, losing stereochemistry. Same issues for the same reasons here. And I think we've already answered this once. In the Markov-Makov reaction, we always put the OH on the more substituted carbon. Is there a case where this doesn't happen? Just like we were talking about, we're going to add anti-Markov-Makov addition today. And there are some, we're going over some of the greatest hits of addition reactions here. We're going through the ones that are pretty well understood, commonly used. There are niche cases too, where like there's very specific reactions that are used that are not maybe commonly used either because they're not as well understood. We will come up against some mechanisms in this class where I'll say this mechanism is just plain out too complicated, or this mechanism is not known. There's some competing hypotheses. And so we try not to teach those that much in the textbook classrooms because what's the point of teaching you something we don't understand yet? So bear in mind that this is far from an exhaustive list of reactions, and if you did go into synthetic organic chemistry, you would do a deep dive into your particular area. There are people that specialize in addition reaction mechanisms and figuring them out, or figuring out how to use them and maximize yield, things like that. It's just a little bit beyond what we're doing at this point. Main thing at this point is that you know that these things exist. So here's our first anti-Markovnikov. It's called hydroboration. And it's another 2 steps. So technically it's hydroboration followed by oxidation. And the main thing is, this one is, it's not, it's stereo selective, not stereo specific. Stereo specific means you can only get one possible enantiomer or one possible product. This is stereo selective, meaning you can get a little bit of the other one mixed in, but 90% yield is going to give you the anti-Markovnikov. And actually, honestly, 90% yield is pretty good. You'll get a trace amounts, single-digit percentage of the Markovnikov and some unreacted product or unreacted reactant. But for the most part, this is your key, right? When you see the boron in the first step, it's hydroboration. Mercury in the first step was your oxymercuration. Right, and it's stereo-specific in that it only results in a syn addition, same as oxymercuration. And it's going to be for the same reason. We're going to wind up doing a stereochemistry inversion and then invert it again, just like before. All right, so but net result is really the only big difference is on the less substituted carbon. Yeah.
It wasn't stereo specific.
So I meant that with regards to which of these is it going to. I said that incorrectly. It's not that it's stereo specific, it's regio selective.
Gotcha.
Regio selective means Markovnikov versus anti-Markovnikov. Stereo selective is talking about which stereo isomer it's in. So it's stereo specific, it's regio selective. Correct, yeah. And I just said stereo selective because that regio did not come to my mind when I was talking in real time. So it's a good catch.
A little bit.
Yeah. Makes a specific constitutional isomer. Stereo is specific stereo isomer. Make sense? All right. So if it's stereo specific and we only get syn addition and it's regio selective and it's anti-Markovnikov, that tells us something about the mechanism, those two things right there. And the fact that we don't get the anti-addition is a very specific point to about the mechanism, just like with the oxymercuration. All right, and so we're going to break this up into 2 steps, just like oxymercuration followed by demercuration, hydroboration followed by oxidation is going to be our 2 mechanism steps here. And they're each kind of big enough to be their own step. And really the trick is that each of them happens 3 times. Because that BH3, basically we're going to come in here to this BH3, this borane, and we're going to replace each of the hydrogens with a carbon boron bond. And so we're gonna do that 3 times. And then the oxidation step does something similar, where now we have a boron with 3 organic molecules all attached to the same boron. So now we have to come in here and remove the boron 3 times. So because of this molecule, basically, we're gonna have a big bracketed section. We say times 2 more times, or times 3. We do this 3 times to get this as our actual intermediate. Right, so borane, it's also worth remembering, borane is one of the few naturally occurring, I'm putting it strongly, few relatively stable compounds that exists without a complete valence. Boron is just not electronegative enough. It's a non-metal technically, but it's not electronegative enough to really to pull electrons away from anything else to complete its own valence. So what you wind up seeing with boron is borane, BH3, doesn't have a complete valence. It's sp2 with an empty p orbital piece. So it basically is like a carbocation except without the charge, which gives us an empty orbital that we can play with. So what we wind up seeing is this sort of weird geometric shape where we can bring in those electrons from the pi bonds, come in and donate electron density to the boron, similar to the way that we did with mercury. And we said, but instead of making a 3-sided ring, we kind of make a 4-sided ring where one of those is the hydrogen. And this is, we talked about that symbol, the double dagger symbol. Does anybody remember what that means? Transition state. So basically brackets the fact that we don't have any complete bonds here, and the fact that it's got this symbol. This symbol means this is a transition state, not an intermediate. So in other words, we're at the top of a potential energy surface. We're at the paths between reactants and products. So basically, we break the pi bond to form a bond between carbon and boron. We break the boron hydrogen bond so that the hydrogen can form a bond to the other carbon, to the more substituted carbon. Still doesn't really explain why we put the hydrogen on the more substituted carbon, unless we think of it kind of like the mercury, breaking up that 3-sided ring structure with the mercury. We brought in our nucleophile to the more substituted carbon because that was the easier bond to break, right? Adding that, we're going to wind up doing the same thing here, adding the hydrogen to the more substituted carbon, because that's the carbon that's going to be more stable sort of instantaneously without a bond. Because it's the more substituted, it'd be the more stable carbocation. It's also going to be the better target for the hydride to come over and move over, just like we said with the mercury. We're just basically doing it backwards. Instead of adding our nucleophile first followed by a hydride, we're adding a hydride first, which means that our hydrogen goes to the more substituted carbon just by switching the order. That effectively switches it Markov-Markov, anti-Markov-Markov.
So it's kind of doing the reduction.
Exactly, it is doing the reduction first. You're exactly right. And so drawing this mechanism, we just kind of do it as 2 arrows. Your pi bond moves over to the boron. Your hydride bond moves over to the more substituted carbon. We basically just do a quick swap. And then you do that 3 times. Because the boron has a total of 3 hydrides on it. So we have 3 different times it can react. So stoichiometry wise, we actually only have to use 1 of these for every 3 molecules of our reactant. Which also makes it relatively, yeah, not bad. And boron's cheap too, for that matter. And so we wind up making this this stable intermediate called a trialkyl borane. Alkyl just means we added some carbons to it, right? Some sp3 carbons are attached to it. And this is totally acceptable way to write it. You can write, do this 2 more times, as long as you show this step first. And this is just a figure kind of showing the sterics and how the electrons behave. If it was anti-Markovnikov, we can keep everything, it's a combination of sterics and that weaker bond to the more substituted carbon. If we tried to add the boron to the more substituted carbon, it's just a little bit more crowded. Boron's not particularly big, but combination of the sterics and the fact that that more substituted carbon is easier to make a bond with a hydrogen means that we're gonna preferentially put the boron on the less substituted carbon. And it's not perfect, like I said, it's a pretty small difference in energy because boron's not that big in that energy difference between the mercury or between adding the hydrogen here versus here. That's not that big of an energy difference, and that's why we only see the 90% yield with this. But that's still significant enough. It turns out with that exponential relationship with activation energy, well, there's 2 aspects to it. Remember this equation, because activation energy is in an exponent, a small change in activation energy can have a pretty big change in rate. And couple that with the fact that A, remember, is our geometric component, is our entropy piece, like what's the probability of these things run into each other properly. So the more crowded it is, the more A is affected by that as well. So it's, even though it's a pretty small difference, both in the activation energy and in the sterics, it's big enough that it'll give us a 90 to 10 ratio of the anti-Markovnikov.
But the Markovnikov still.
You'll have some small amounts of it.
And that's through this like first hydroboronation state.
Correct.
Yeah.
Because this first step where we attach the carbon to the boron happens with the boron going to the less substituted.
But sometimes you can go to the more substituted.
We're not gonna spend a whole lot of time thinking about, we wanna keep it in mind in
Yeah.
terms of everything that can happen, does
But
happen.
you kind of want to assume that it's just
Right.
Markovnikov from.
Yeah, exactly.
That's why it's regio selective, it's like, we'll have.
Right.
Like,
Right, and that's why we used to call it regio-selective, not regio-specific. Regio-specific only means only one is possible. And regio-selective means there's a preference. And same with stereo-selective versus stereo-specific. We'll see that same terminology come up with stereoisomers too. It prefers this one, but you can get some of the others versus you will only get one stereoisomer.
there's a lot of different categories of all the additional reactions.
It is. This is why this is a whole year-long course, right? And why we're gonna spend probably, we'll be doing addition reactions pretty much until midterm, because we're gonna add alkynes once we get done with alkenes. Alkynes have their own categories of addition reactions that are related, but just different enough. So we'll get really familiar with this vocabulary the more we spend time with it, right? There's also a reason I'm not giving you your midterm at the end of this week, because you're just learning this. All right. The oxidation step, once you've made, this is actually the trickiest part here. That first step, the hydroboration step, is actually not all that bad, right? It's a little bit weird. The oxidation step is trickier. So basically, if you, let me go back to, I'll go forward for a second. The second step where you have hydrogen peroxide and sodium hydroxide together seems like it's a pretty nasty mix, because it is. Sodium hydroxide is already nasty and hydrogen peroxide is already nasty. We put them together to make it even worse. And so what you wind up seeing is you wind up deprotonating the hydrogen peroxide. So the hydrogen peroxide has a pKa of about 11.8. So if we add enough sodium hydroxide, we can wind up making a hydrogen peroxide ion. Now, hydrogen peroxide ion is an even better nucleophile than hydroxide is. And it has this weak oxygen to oxygen bond. An oxygen to oxygen single bond gets its own category, particularly because it's very weak. When you do this, this makes it so that this oxygen can come in and attack the bromine, or sorry, the boron. And it can do so without a leaving group leaving, because remember the key aspect of that boron is that it's got an empty p orbital just sitting there. So you go from being trigonal planar to being tetrahedral temporarily. And then it just does a quick rearrangement. Basically, you attach your peroxide ion, the boron, for a second, and then it's basically a methyl shift. Except you basically move the entire R group over to the oxygen and kick off a hydroxide. So the net result of this is you basically took your R groups that were attached to your boron and you just inserted an oxygen in between the carbon and the boron. I do like when chemists, when they're describing mechanisms and things like that, they get colorful with the language. This is actually the right chemical term. It expels the hydroxide, it causes the expulsion of the hydroxide. Alright, so deprotonate the hydrogen peroxide. Hydrogen peroxide can now act as a really strong nucleophile to come into the boron. But it's a really strong nucleophile with a really weak oxygen-oxygen bond. And that really weak oxygen-oxygen bond basically kicks one of the oxygens off and you move your R group over to get. And so compared to where we started, you just added an oxygen in between the R and the B.
Is that kind of driven by the difference in electronegativity between
100%. My friend in undergrad did I wanted to do my undergrad research in physical chemistry, which wasn't as useful as it sounds, or fun as it sounds. My friends did theirs in organic chemistry. And after they'd spent a summer doing research on synthetic organic chemistry, she said the answer to every why question in organic chemistry is electronegativity. You can almost always trace it back to electronegativity. It might be a couple steps removed, but it's never wrong. Sometimes it's just not specific enough. But yeah, the difference in electronegativity, you've got a boron to carbon bond, but oxygen is more electronegative. So basically, instead of an oxygen sharing electrons with another oxygen, that's two bullies fighting over the same toys, right? So basically inserts itself in between two weaker atoms.
Bully's baby boron.
Bullies, baby boron, and middle schooler carbon. And you get this instead. And your other bully leaves to go bully someone else. Right, and once again, because we have three R groups attached to the boron, we see it 3 times in a row. And so we wind up with this, it's not a trialkyl borane anymore, it's a trialkoxy borane.
Would it be wrong to throw just another arrow on your name with that? Or is that
We get another, so like this.
I mean, that's 2 separate arrows.
Oh, I would look at that and see the same thing. That's fine. Yeah, arrows are tricky with chemistry, right? And then once we do that, we basically go to the more extreme case, which is we continue to oxidize the boron. And we have now this hydroxide is still a strong enough nucleophile they can come in and attack the boron again. And we just wind up with nucleophilic attack followed by leaving group leaves 3 times in a row. Right, so your hydroxide comes in, attaches to the boron. Now we have a tetrahedral boron again. And that just means that these are pretty good leaving groups. So we wound up adding the OH. That means one of our OR groups can leave, one of our alkoxy groups can leave. And once again, that happens 3 times. And so it cuts off a little bit at the bottom, but our final result after this one is we're gonna have 3 alkoxy ions, which just need a quick proton transfer to make them alcohols. And wind up this trihydroxide boron
That's after it's 3.
after it does it 3 times again. Which really would not stop at this, we wind up making a borate molecule. Which then can continue to become more stable by going through
Which
more rearrangements.
that's the end, so.
So then we never want to leave it as a negative charge on our final product, but all it takes is a quick proton transfer. So something. That if there's water, so we're doing this in water. So we just have water act as a proton source. So R minus plus water. So we get 3 alcohols. And specifically, the oxygen is attached where the boron was attached, right? So we attach the boron to the less substituted carbon, which means our oxygen gets attached to the less substituted carbon. That's the twist that allows us to make this an anti-Markov competition. It's still adding in the same order, add to the more substituted than the less substituted. It's just switching what we add first. We added the hydride first in this case, not the oxygen first. Right, so that's it's a lot of steps.
There's more.
And well, so that's this step, I didn't shrink this down enough.
Oh, I see.
But it's just, you're leaving group leaves and then you do a proton transfer. There.
Well, that's just where you double bond and put no H on the end of it.
Right. But we'll find out that having these things very, like being able to be this specific about it is really powerful, right? Especially when we start doing more. Yeah, no worries. I didn't realize it wasn't on before. I just wasn't paying attention. You don't know it's not there till you need it, right? All right, so we'll go ahead and take our break there. When we come back, we'll do a couple practice problems, but I'll leave the mechanism up for now too. And remember that these PDFs are online as well. This is the way that our old textbook did mechanisms. I really like how clearly laid out everything is. The OpenStax, it is free, but it's not as good at mechanisms. There's certain things it does better. But there are certain things that the $300 textbook does better, and mechanisms specifically is one.
Bradley showed me the old textbook, and it's a hell of a lot better.
And I would never advocate for pirating copyrighted material. But I know that there's a PDF version of this textbook floating around somewhere. And somebody who's taken this class before might have access to that and know where you could find a copy if you wanted to break the law, which I do not advocate.
So looking at this in general.
One of the more important things I learned in college is plausible deniability.
Let the record show.
Let the record show, your OChem instructor said, don't do this. Don't do this thing, that's very, very helpful,
Plan something.
right? I have- Copyright bothers me on general principle in general, because I don't think, one. Science faculty, especially community colleges, believe in free flow of information. And then, two, the way that they're turning all of our digital purchases into this subscription model, and like how you can. If buying something on digital copy on Amazon is not really buying it because it can go away at any point, then pirating isn't really stealing.
Yeah. I don't know, the laws,
Delete it off your thing.
the laws for that are extremely swell.
Right.
Internet laws, they haven't updated that since like the late nineties.
And
So-
that's because, except to make them more strict.
Right.
With the DMCA and stuff like that, but, and that's entirely because the copyright holders are big pockets. All right, let's take our break. Let's come back at, I'll give you an extra couple minutes. We'll come back at 3 after.
Will we go over the mass spec lab?
We can.
There was
Yes.
just one thing that made me want to strangle mass spectrometry, so.
Yeah, we'll do, I think we'll have some time in lab today. There'll be some downtime while you're waiting for a reaction to happen. We'll talk about it then.
Awesome, thank you.
Yeah, no worries.
Thanks for saying.
It was pretty chill.
Pretty chill?
Yeah.
That's good.
How was yours?
Good. And. Yeah, it was fairly busy, but not too busy.
We went to
there's a conference this weekend, and then I just honestly spent a bunch of time studying for the most part. It was cool. But yeah, I'm excited for tomorrow morning. I'm leaving to go back to Pioneer. My mom and grandma. There's a bunch of projects to do there. Then next week when I come back, I'll have time to go wander around. Or we go over the Wednesday long picture. I think it's still, this would be good, this would last, you see that here? This, shoot up here.
Well, we read that.
It's like a couple of onitis, up above Pioneer Trail. That's real, you know what that is? It's like, yeah. It's, no. Just studying your rules, pretty interesting. Oh, cool. It's let's see what we're at. Three, what you said. Yeah, that's field. No, field. So we're here. So if you go down, there's Pioneer Trail. Right here, if you're going like out of town on 50, there's Pioneer Trail. And then there's this little road here at Midas. And so you park like right here, and then you can follow this little road in, and then just walk along it, and it links you up to all these trails. And then if you go, this is the road I went on here.
Oh, nice.
Yeah. And then I just walked up this thing. Yeah. I have my little rescue beacon thing, so if I really fuck up.
Oh, dude, I used to go up to Trailer Peak, just alone, and just camp.
Oh, that's where I was at. That's no schedule.
I know. Yeah, I'm on the weekend.
Yeah, I just went on the connector and then just walked up this bridge here.
Yeah, I just go up that. Yeah, I usually just go up that, just go Trout Creek. Well, I used to just fucking haul up that.
I got
It's nice because my feel like I need to drink, I'll just fucking go in over. You can get stuck up there?
I got stuck in a crevice when we were rock climbing. I didn't have a rope or nothing. Well, I know my buddy had a rope and he just had to drop it in. Follow me out. It was more of my own rescue mission.
Wow,
Once he threw the rope and he's like, "You're on your own." Yeah, but I mean, it was no big deal. It's not-
It's all sweet. I don't know if I can be able to find trout.
No, not right now.
Yeah.
Actually,
I put snowshoes on above the 8500.
Yeah, well, it's not really facing the sun too much. So, and there's a lot of trees out there too.
Yeah.
If you don't know where you're going, you kind of up the creek.
If you follow this guy, if you follow all the fucking rivers down, it generally leads to the trail that goes.
Yeah.
That high limit, right? I remember this going to.
Yeah.
To the other side.
But yeah, you can, I think High Meadows will get you there.
You can go many different ways, so.
Yeah.
You can fucking drive down, what is it, like 89, 88 road.
Yeah.
There's like little, that little side hole and just fucking.
Yeah, through the woods, through that, there's a meadow
That's
right
like
there.
10 miles. That one's not.
I got kind of a late start. I was like, I think I got to the trailhead at like 9 AM for that one, but I think next week I'm gonna try to get there at like 5:30 and then go do the same one, walk over to Trimmer and then hit Friel and then just kill myself. It's so tired. Yeah, because they're all connected, like, and they're all totally see where you can get over.
Yeah.
The terrain's not that bad. I kind of looked at it. It's not really scary.
Trevor Beach probably the same.
Yeah, I was looking at that, like the south face of it, there's some like, really good looking granite.
Yeah, facing like towards Myers.
Yeah,
Yeah, that spot's sick.
Yeah.
If they are facing towards Myers, or, cause I was looking
Is
at.
that not south? I don't know.
They're facing towards like Myers is like over here,
So this is east, and then.
And the south would be facing towards like a lookout.
Yeah.
what GPS app?
I use a bunch of them, but this one's.
Yeah.
Two Gaia, two.
Oh, I use guys,
Yeah. Yeah, cause I was looking at the south side of it, which. That one, I think I might have gotten a decent photo of it.
It's not scary. That whole.
Dude, that's what
area.
It was so cool. But yeah, so.
It's scary though sometimes.
Like this side.
Dude, look at that. Oh
Nice.
my god.
Yeah.
We grew some like.
Yeah, it's up here somewhere, there's like a little crevice that's up there, it's like 75 feet down, I just climbed into it, not thinking that I could probably. out there.
Yeah.
And I was just screaming, ah, hey, someone threw a rope in.
I would want a partner in track, actually. Find this.
Yeah, we do most of like free climbing, no ropes or nothing like that. We
Yeah.
bring.
Well, we got sports stuff. Yeah, we do it on anything for.
It's a lot of fun.
Yeah, I mean,
Find stuff. I can't.
I could find.
I would like free solo a like 30-foot tall 5'5", like something like that.
I did what was ranked to 5'14", barefoot, no rope, no harness, just boxers. It was just like my boxers on barefoot, yeah, when I got to the top, it was 75 feet, it was 5'14", free soloed it, and when I got to the top, my feet were fucking bleeding. So I'm just trying to get the footholds.
Is there even a 5'14"? 5'14" is like.
That's what they
like.
labeled it as on there.
Well, I don't know.
Like 5 years ago.
I doubt that's
So
right.
That's what they labeled it as, that's what it
You
is.
know, It's like the nose on Hellcat is like.
I'll show you.
Yeah, that's not, that hard is high up there.
No, it's hard.
That's what it's, dude.
5'12" is really hard. Have you seen like the movies of Connell doing, like some of the moves on it?
Have you not seen like the scale difference in the past like 5 years? The scale,
Yeah.
difference, there used to be like 5'7" ones. And now it's
Yeah,
like
yeah, yeah.
changed.
Oh, okay, so it's old school.
Old school, they said it was 5'14" on the app, I was like, I don't believe this. That's why I don't know.
Yeah.
There's a 5'14".
Is there?
Dude, that thing is.
There's no way I can find that.
Oh, I mean, it's a sport route.
Yeah, I would want to, I would try it on top rope and then get up like 40.
Oh, there's no way you can do top rope on that.
Oh, really? There's no height.
Where's that?
I'll show you.
Yeah, I top rope this, I'm talking about like, probably 70 times before I tried.
Oh,
it.
nice.
Yeah,
Cascade Cliff.
but I did it without shoes, because my friend said I was pussy. If I did it with shoes, I was like, no, I'm not, I'm going barefoot, like.
Weekend at
You can be
I have
You're gonna feel it burn.
And then recently,
Oh,
I'm going through the last year and 2 years ago. 2 years ago, it was great. And I was, next week is like-
Was it like a tiny little finger crack or what's it?
So I don't know what it is for next week.
I'll take a look at it.
Yeah, and then, or if you want to invite me to the campus show.
Sorry, I forgot I hadn't done that yet.
Yeah.
I will do that today
At-
at
May.
Mail. Yeah. Sounds good. Thank you, Mario.
So Cascade Cliff. So it's the bay, parking lot, I all the way up. And you take a little detour.
It's kind of space black.
Yeah, I've heard of that spot. I've heard of people getting hurt right there.
I've only done rescue, that's successful.
That's about what I was looking at.
5-10 feet. I mean, dude, that thing is hard. That thing's hard.
Yeah, it's like 3 years. It's so long. I keep the dog up.
One of my friends, Levi, he did blue sky. Yeah.
All right, let's get back to it. I'm okay with this taking a little bit longer. We're making good time on these.
Yeah.
So I'm okay with us finishing the conversation there. So categorization for this one, when you see this collection, it's hydration, anti-Markovnikov, no rearrangement. And so if you can think of it in terms of that, that's sort of a useful way to You can think of it like taxonomy to some extent. Right, categorize these things, and then you don't need to think about the mechanism every time just to get to the product. Hydration, anti-Markovnikov, to the less substituted carbon. And we did add a hydrogen to the more substituted carbon, but the skeletal structure we don't usually show.
Sorry, it might be the THF.
Sorry, THF is just a solvent.
Oh,
Tetrahydrofuran, it's just a solvent that's a non-polar, I'd say polar aprotic solvent. That allows this to happen. The problem is that borane is pretty reactive with anything that's protic. And so we wind up, if you mix borane and water, you just get hydrogen and hydroxide, hydrogen gas and hydroxide. So we just have to make sure we're doing this in aprotic solvents. THF is a really common one. For this particular reaction. And again, likely other aprotic solvents would work. You know, likely that they've just tested a bunch of them, and this is the one that gives best result or has the best properties relative to how toxic the solvent is and things like that as well. And this one also doesn't really have a way that lends itself to switching out the nucleophiles. You can't really use this very well as an ether synthesis. Like the way we did with the oxymercuration, we could just swap out the water for any nucleophile we wanted for the second step, for the second part of it. This one doesn't work as well because you need this step, you need that peroxide. You could probably use a peroxy ether. To do something, but it's good. So instead of H2O2, you could say ROOR. Or ROOH anyway, because you need to be able to deprotonate that peroxide for this to work. So you might be able to do it, but it's a lot less common because these are particularly nasty to work with as well.
So from our example that we did last time, with break, so this would be considered one of the R groups that's made.
So this
That
whole piece would be the R.
yeah,
Yeah. So,
okay,
yeah. So R in general is just any is a placeholder.
right,
We could put, in theory, you could do a peroxy alcohol. For this second step and then make it an ether out of it. But again, less common, nasty to work with. Not
and the
like this.
hydrogen on the alcohol is constantly doing like a proton transfer with the other.
Because we're in basic conditions.
Because you're in
right?
basic conditions, yeah.
So and realistically, the next step after we will do these two things is we're gonna take it, we're gonna neutralize the solution by adding some weak acid or adding water to it. To try and, because we don't wanna store it at basic conditions.
Yeah, I was just wondering, just like kind of piece everything together.
Yeah,
So you can't have an anti-Markovnikov as a Roman issue. Right, you just need oxygen.
it has to go through a different mechanism. Turns out we can, we're not there. And we'll talk about just straight bromination, which adds two bromines, one bromine to each side. Well, and iodination does the same thing. So, well, we're getting there. Makes it really easy for me to write these questions, because I just mix and match the arrows with the other, I don't have to redraw the structures every time I take this problem, and I switch these arrows out, the oxymercuration one, and you get an opposite product, right? So just don't overthink it. We're not doing anything yet where we're changing where the carbons are, so always start by redrawing your carbons in the same spot. And then it's just a matter of, we're breaking up pi bonds. What are we adding to each side of the pi bond? And you can also see how controlling Markovnikov versus anti-Markovnikov and using elimination reactions together, we can make a pi bond And then we can put the OH where we want it. And then we can do another elimination reaction. We can actually control whether by using the Zaitsev product versus Hoffman product, we can actually move a functional group around. If we started here and we decided we wanted to put our OH here, we could do an elimination reaction to make this. Then we could do Markovnikov to put an OH here, or put a bromine there since bromine's a better leaving group. Then we could do another elimination reaction where we make the Zaitsev product, which is going to put the pi bond here. And then we
So
can
then
do
you're
the
just shifting-
anti-Markovnikov. So yeah, we can basically use successive eliminations and additions by controlling Zaitsev versus Hoffman and controlling Markovnikov versus anti-Markovnikov. We can actually move stuff around with a high degree of specificity.
What would the yield be like?
It would be pretty low yield.
Yeah.
Unless we were pretty careful, right? Because every successive set of reactions is gonna lower your total yield, but it's doable. And there are some, this is one of the reasons why some pharmaceuticals are particularly expensive. If the only way to make that pharmaceutical gives you, the synthesis pathway gives you a 12% yield, that's gonna be really expensive because they're not getting much product for everything they're putting in, and probably it's a lot of steps along the way, which is a lot of manpower and machinery as well. So there's, again, with the IP conversation, I don't like the idea of patenting chemical structures because that goes against everything that I hold dear. But you can see why in a capitalist society, why we have rules about IP, intellectual property for pharmaceuticals, because you have to develop the production and then the companies actually have to fund the study that decides whether or not something is safe. All the studies and all the tests and human testing and side effects and all that, the companies have to put forth all of the capital to start that. That's why you don't have the startup pharmaceutical companies really, right? If you do, they're coming out of grad school programs where somebody has figured out a decent synthesis for something they think is useful. And so then they can get investors to buy into it. But in general, you don't have somebody in their garage starting a pharmaceutical company, right? Because it just
Usually explodes.
it just usually explodes and it's usually illegal. And they're not going to the FDA. We'll just start with that.
I've only seen successes. I don't know. I just see the consequences. It's not the process, it's the people, you guys.
All right, so let's think about it from the other side. Let's say we've got C5H10. There's only so many formulas or so many structures that can match that formula, right? 1 degree of unsaturation, so we know we either have a pi bond or a ring structure. So we know that this is the formula, but we don't know what it is. One of the ways that you can figure out what it is, besides taking an NMR of it, is to actually try and react it. And it's an unsaturated hydrocarbon, so it's either an alkene or a ring. If it's not cyclopentane, because you can just go take the boiling point of your unknown to see if it's cyclopentane or not. If it's not that, then you can be pretty sure it's an alkene. So we take compound A and we put it through an anti-Markovnikov hydration, and we get something we actually can characterize. What was the starting material?
Not the OH off and throw it up with one.
Yeah. It's helpful to think about these reactions as happening backwards sometimes, especially when we get into synthesis problems, but this is another semi-real. Realistically, these days, you're just gonna go to if you're doing this in research and you have this unknown, you're just gonna go to your buddy's lab who has an NMR that he can get you access to. If your lab doesn't have their own NMR. And because we had the NMR of this, it'd be pretty easy to figure out what it was. But this is another way to do it that's a little, if you don't have access to some of those resources, is okay, well, what happens when I do this reaction. I know what this mechanism does, I just don't know what I started from. And work backward that way. So then. Actually, last slide is what happens when we have a mixture of all possibilities. We just have to keep everything straight. So I'll give you a few minutes. Yeah, I thought I went through and cropped all these so that the question marks weren't showing, since that's easier to. Right, so none of these is inherently difficult. It's just a matter of keeping all your variables straight, right? This is one of the reasons why we do spend so much time on the vocab aspect of this, is because the more you can get the right wording down, the easier it is to remember the various wrinkles involved, right? So, hydroboration, followed by oxidation, hydration, anti-Markov, no rearrangement. There's our product. Acid catalyzed hydration. It doesn't say plus water, but H3O plus written that way. Excuse me. Excuse me. So. Goes through carbocation intermediate. And then it's gonna be Markov with rearrangement. Are we gonna have to worry about rearrangement here? No, because both the other two nearby are secondary. So we're gonna put our carbocation on the tertiary. It's gonna stay there. It's 2 carbons. There's our intermediate. There's our product. R plus S. Is now we did create a stereoisomer or a stereocenter. there really any difference between A and H here? Just that one extra methyl group. You're gonna wind up with. Mechanism's not different exactly. So we just get that instead.
But that does give us a chiral center.
That does give us a chiral center, so R plus S. Only one chiral center. If we had those two extra methyls like right above, now all of a sudden we added two chiral centers and we have to worry about, do we make all four of them or do we only make? Then we have to start thinking about, okay, it's a syn addition. So we're only gonna make two of the four stereoisters.
You have to simplify like. And say this was. First order pathway, and then second order would be next step, would it be? R plus S would signify for one piece of it, and the other piece would be.
You can have reactions that are a mixture of achiral and stereospecific. This isn't one of them though. We would actually just have to track through the method. So because we wind up with it being. It's because it's a syn addition. We would get this and the stereoisomer where both of those are down. We would not get where the hydrogen's up and the oxygen's down. There are some cases where you get stereospecific in one part but not the other, and actually the next reaction we're going to look at, which I might just let you out a little bit early today instead of jumping into a new mechanism. They're moving fast. We very specifically get only anti-addition, but can create two stereocenters. And that actually tells us something about the mechanism, where we'll use that piece of information to rule out one possible mechanism. And then over here, we've got oxymercuration with water. So it's hydration, Markov of no rearrangement. The only ones that'll do rearrangement are the acid catalyzed ones. So HBr, HCl, H3O plus. No, exactly, because that mercury makes that three-sided ring. Right, so then we would wind up, Markov means we add the oxygen to the more substituted carbon. If we did this, this is the same molecule that we did for one of our quiz questions with acid catalyzed. And we did see a methyl shift. Right, which if you know that that's going to happen and you want it to happen, you can use that. There's a reason why we teach both of these. It's not just because this is the easy mechanism, so we do this first. It's also because there's certain times where you want the rearrangement. The trick with rearrangement is really hard to undo. Once you do a rearrangement and change that carbon structure, it's hard to get the back the way it was, especially methyl shift.
That's all down.
Right, it's all downhill in energy. It's hard to go back up in energy. We will add the last tomorrow or Thursday is the last lecture on alkenes. On addition reactions, and we will talk about changing the carbon structure. Once we get past addition reactions, there's actually a class of reactions that allow us to use a pi bond to break a carbon skeleton apart. Basically, you can chop it at the pi bond, which adds a whole nother, like, that's not just another tool, that's a whole nother workshop. When we can change the carbon structure. So
if we add a pi bond where we want.
We add a pi bond where we want and then do the oxidative cleavage and then cut it right there. Yeah, you can cause
ultra specific.
right. And then we just need some tools to be able to add carbons, and then there really is no limit. We'll add those pretty quickly too when we get into alkynes. So we'll spend some time on synthesis before the midterm too. alkenes, alkynes, and then how do we use these tools, because we have a lot of them, so. The last one here. Acid catalyzed, so rearrangement, possibly. Markov-Nikov. Adding a bromine, not a hydrogen, not an oxygen. So. Put all of our carbons back where they go. No need to worry about rearrangement because we're already a tertiary carbon.
And there's no.
Right, and really, even though with those metals, you still are only gonna see that. If it's going to take you from being a secondary carbocation to a tertiary, you're not gonna see that. If you're already tertiary.
Yeah.
That's one of the nice things about, if we start with a tertiary carbocation, you don't even have to worry about rearrangement. It's already a stable, I guess the only possible case is if there's resonance. That could throw a wrench in things as well, but that's not a true rearrangement then, right? All right, so questions on these? It's really only 3 mechanisms, but 2 of them are kind of tricky. And as far as just predicting the products, it's not so bad. Just remember the classifications are, is it hydration or some other addition? Is it Markov-Nikov or anti-Markov-Nikov? Do I need to worry about rearrangement? All right.
Do you have notes?
That's a good point. Mariella just came in here. Let's see if she has printed them out. If not, I'll go print them real quick and you can read up on that.
Thank you.
That's a really good thought. Thank you.
It seems. It seems not that bad.
It's all about.
We're just doing like SN1, SN2 reactions and just like observing reaction rates.
Oh,
Different shit. So it's not very.
I'm gonna go to.
All right, this is a good one to have ahead of time too, because this one you're gonna make your own data tables. So basically, it's just a substitution reaction that we're gonna look at. We're just gonna swap out what the substituent is, so we can compare things that we talked about theoretically. Like, what's the rate in an SN2 reaction, primary versus secondary versus tertiary? Right, so you're actually gonna get the experimental data. We're gonna do substitution reaction on a tertiary carbocation and under SN2 conditions, and you're gonna see nothing happens. It's pretty much all gonna match up with what you're expecting. So if you keep that in mind, those are the 2 main variables. Where is your leaving group? And are we doing this in SN1 conditions or SN2 conditions? But so you're gonna want to go through here and look at each of these. It's an experiment 1, experiment 2, etc. Think about what variable is changing in that experiment. Like for experiment 1, it has you doing 1 bromobutane and 2 bromobutane. So that's a primary versus a secondary, right? And so you're comparing you're comparing the rates for primary versus secondary versus tertiary. And then experiment 2 changes a different variable. So basically, you're gonna go through and make your data tables, like, and you're basically just gonna be, how long does it take for the reaction to happen? It's gonna be, so a slow rate is gonna have a long time. It'll be 10 minutes maybe. One of them is so slow it can't be measured, right? So one of these, the SN2 reaction on a tertiary substrate, we're not gonna expect that to happen at all, but you still might want to start that one first, just so you can leave it and check it at the end of lab. But, so if you come in with an idea of what to do, get most of your data in about 2 hours for this one. And we'll go from there. Okay, so I'll open up lab at 1 and we'll have time to go get a bagel or something.
Or you don't have more than much?
It's gonna go.
Yokes.